welcome to the workshop today on the introduction to image segmentation, 3D reconstruction, and VR visualization. My name is Ronell Sicat, and I'm a visualization scientist at the KAUST Visualization Core Lab. We are joined today by my colleague, Thomas Teusel, who will help us keep track of the questions in the chat. So yeah, KAUST Visualization Core Lab, or KVL, is a part of the KAUST Core Labs and the research infrastructure. And in KVL, we provide expert support in data visualization and data science. So I listed here a bunch of the topics that we cover in KVL. And the focus for today is, or are the topics here in the lower left. Now, aside from expert support, we also provide state-of-the-art visualization facilities, such as this high-resolution display and several virtual reality facilities. And for today, we will actually have a look at how to use the virtual reality head-mounted devices, or HMDs. So yeah, if you want to find out more about KVL's services and resources, you can go ahead and visit our website. And if you need help with data visualization or data science, you can contact us at this email address. Okay. So yeah, our outline for today's workshop is as follows. So we're going to start with an overview of the whole workflow from segmentation to reconstruction and visualization. And then we're going to go, so together with the overview, I will actually sort of describe some of the basics in Avizo, because we will use Avizo most of the time. So it's important to get the basics down in the beginning. And then we're going to go dive deeper into image segmentation. So first, we're going to use Avizo, and then we're going to use an alternative application called Ilastik. And then we're going to go to 3D reconstruction, and finally, VR visualization. So I just wanted to mention that for each part here, I'm going to be playing a pre-recorded video. And then after the video, or even during, you can post questions in the chat. And me and my colleague Tom will try to answer your questions in the chat. Or if there's time, we can also discuss after every part. Okay, so with that, I'll go ahead and start with the first part. The starting point of our workflow is the input data, which in our case is an image stack, as you can see here. In an image stack, each image corresponds to a slice of a 3D object or sample that you would like to analyze. This can be anything from a mouse brain tissue, rock sample, or in this case, a pack of sand particles. Image stacks like this are typically acquired through imaging techniques such as microscopy and tomography. This particular example here is a CT scan of a small pack of sand. And as you can probably imagine, the low intensity or dark colored pixels here correspond to air pockets, while the high intensity or bright colored pixels here correspond to sand particles. With that being said, image stacks can be represented using a wide variety of formats. In this particular example, each slice is encoded as a TIFF image, where each pixel is a 16-bit unsigned integer. This means that pixel values will be in the range between 0 and 65,535. Keep in mind that this is just an example, so your data can have a different format. For instance, you might have an 8-bit unsigned integer per pixel, which will give you a smaller range of 0 to 255. Now, given the input image stack, the first thing we want to do is to separate the different classes or materials in the data using segmentation. Segmentation assigns each pixel of an image to a label, thus partitioning the image into different classes or materials. So in our sand example here, the result of segmentation will be the label images here, where the two segmented materials, air and sand, have been color-coded. Label images are usually encoded using 8 or 16-bit unsigned integers, where non-zero values correspond to materials, and 0 corresponds to unassigned pixels. So here, for instance, a label of 1 can correspond to air, and 2 can correspond to sand. Now, once we have our label images, the next step in our workflow is to generate a 3D model of the materials that we are interested in. We do this using the reconstruction step that gives us a 3D model, typically represented as a triangular mesh. Finally, we can then use the extracted 3D model for visualization and quantitative analysis, either on the desktop or in virtual reality. While for most applications, visualization on the desktop is sufficient, having the ability to visualize and interact with your data in VR can provide a unique perspective and experience. And the nice thing about our workflow is that you won't have to write a single line of code to bring your data to VR. So it's very easy, as you will see very soon. Okay, so from this point onwards, I want you to keep a mental picture of this slide, because we will keep going back to the terminology we discussed here throughout the workshop. So the main tool that we will use today is Avizo version 2021.2. Avizo is a commercial software for visualization and analysis of scientific data. The installer and installation instructions are available from the KAUST IT website. My assumption is that some of you have not used Avizo yet, so later on I will go through some of its basic functionalities that we will need for today's workshop. If you are interested in learning more about Avizo, KVL has a YouTube video where you can watch an introductory training on Avizo. Now, don't worry about remembering these links because they are all provided in the workshop website. Okay, so when you start Avizo, this is what you get in the beginning. So we are presented with a bunch of options. So you can open a dataset, open a project, or start with a blank project. You also have here a list of recent projects and datasets for convenience. And right now, if you don't know what a project is, that's totally fine. We will get back to that later on. So for now, we will open a new dataset. So before I forget, I just wanted to mention that all the datasets that we will use in today's workshop are available for download at the workshop website. All right, so now let's go ahead and go to the SAND CT folder. And here you'll see a bunch of images, right? And as you can imagine, each image here corresponds to a slice in our image stack data. And you'll also notice that there's some sort of file naming convention that's being used here, right? So all the images here have the same first set of characters, and they all end with a number. And the number here is very important because it tells us which slice the image is within the image stack. Okay, so for now, let's press Ctrl-A to select all the images in the folder and click Open. Okay, so now we get this prompt from Avizo that tells us something about our dataset. So it tells us that we have 128 files or 128 slices, and each slice has 128 by 128 pixels and one channel and one timestamp. So you also have the option here, if your dataset has multiple channels, You can perform an optional channel conversion here, but since we only have one channel, we don't have any other option here. And you can also optionally specify a different name for your data object. But for now, we'll just leave it as it is. You can also specify the units used in your dataset. So here you have the option to specify that. So if, for example, your dataset is within the nanometer scale, micrometer, you can specify that here. For our sand dataset, I will stick with the default millimeter. And similarly, you can specify the voxel size. So by default, the voxel size is set to 1 by 1 by 1 millimeter per voxel. Or if you know the size of your dataset, you can also specify that here. So for instance, if I know that my sand pack data is 200 millimeter by 200 millimeter by 200 millimeter in size, I can just specify that here, and the voxel size will get adjusted accordingly. So for now, let's stick with the default 1 by 1 by 1 millimeter per voxel and click OK. So once the data has been successfully loaded, you should see something like this. And here we can see some of the main views or windows in Avizo. So on the top left, we have what's called a project view. On the bottom left, we have the properties area or properties window. And on the right, we have the main 3D viewer. The project view contains small icons, as you can see here, where the icons are a representation of your data objects and what's called Avizo modules. And these modules, they can perform computation on your data objects to generate new data objects, or they can also perform visualization, such as this orthoslice, and the result of that visualization gets displayed on the 3D viewer here. And the properties window, on the other hand, shows you the different parameters that you can change for the currently selected or active object in the project view. So for example, right now I have the orthoslice object selected. So you can see the corresponding parameters in the properties window that I can modify. So if I click, for example, on the data object, so you can see that the properties window was updated to show us the information about our data object. And now let's switch back to the orthoslice object or module and try to change the slice number parameter. So as you can see, while I update or change the parameters of the orthoslice in the properties window, the viewer gets updated accordingly and interactively. Right? So for example, I can change the slice orientation. So I won't go through all the parameters here of the orthoslice, but we'll sort of try to describe some of them later on as we use them. All right, so how do we create or add new objects or modules in the project view? So we've already seen how to create data object. So we did that before. So here we click Open Data, and that created this data object here. And you probably noticed that Avizo automatically generated and connected this orthoslice to our data object just to have something to show in the beginning. And that's quite nice, I think. And the other option for loading new data sets or creating new data objects in the project view is by clicking this Open Data button, which you can see here, or right-clicking on the project view and clicking Open Data here. So that's for creating new data objects. And Now let's say you want to add new modules connected to this data object. Let's say you want to show, let's say, the bounding box of this data object. So you can click on this circle icon here on the right of the object. And this should give you a list of modules that you can attach to this data object. So in the middle column here, for instance, you can see some of the favorites or most commonly used modules for this type of data object. So I think that's really nice because it sort of gives you quick access to the most commonly used modules. So let's say, for instance, I'm interested in seeing the bounding box. So I click that, and now I have the option to find out more about this bounding box. So let's try that for now. Let's click more info. So this opens up this help window, which I think is really nice because it gives you then sort of the description of the module. So what does it do, and the ports, or sort of the parameters that you can modify in the properties window and what they mean. So that's really helpful. So for now, let's close this one and again try to add the bounding box here. And this time we'll click create. And this creates this new bounding box icon here, and it's automatically connected to the data object in here. And as you can see here on the viewer window, the bounding box showed up automatically. And because the bounding box object is selected here, now you can see the corresponding parameters here on the properties window. Okay, so the next thing that I wanted to show you is how to interact with our 3D viewer here. And to help us with that, we have a bunch of icons here on top that would help us interact with the viewer. So you have your typical translation, zoom, and rotation here. And now what I find myself using most of the time is this trackball option. So what this allows me to do is to quickly do rotation, translation, and zooming using my mouse. So to rotate, I just left click and drag anywhere in the view to rotate. And to pan or translate, I just click and drag the mouse wheel button or mouse middle button. And to zoom in and out, I just use the mouse wheel button. So this is very convenient. Instead of switching or clicking these buttons here, I can just use the trackball option and use my mouse. Now there's another option here, which is interact. So what this allows me to do is, for some display modules, I can now interact directly with the display module and change some of their parameters. So for example, for this ortho slice here, if I click on the slice, I can now left click and drag to change the slice number. So if we click the ortho slice module here and observe the slice number, you can see that I can change it directly if the interact option here is enabled. Okay, that's very convenient. Now the other option I wanted to show you is this view all button. So basically, if, for example, you're super zoomed in on your object and you just want to zoom out so that you see all of the object, you can click this button. So it resets to a zoom level where the whole object is visible. Then you also have these options to view the object from some predefined directions, like this one that's perpendicular to the XY plane, XZ or YZ. We can also change the projection from perspective to orthographic. Okay, I think that's it for now in terms of the basics of using the Avizo interface. And if anything new comes up later, I'll try to describe it. In any case, I highly recommend that you go through the user's guide that's accessible through this help menu here. And whenever you have new modules or data objects in your project view, you can also just click that module and click this question mark button here to see the relevant documentation on that module. So that's very convenient. I actually use that a lot. All right, so now we'll actually get into the workflow that we were discussing earlier, which is segmentation, reconstruction, and visualization. Okay, so again, we will work with this very simple sand CT scan data set. And what I usually want to do before I perform segmentation is get a general feeling or general view of my data. So in this case, we can go through the slices using this ortho slice view, just to get a feeling of, okay, how does my data look like? Do I need to pre-process the images, or what kind of segmentation techniques would be best to use for the data set, and things like that. Now, sometimes the ortho slice is not enough to get a general feeling of the data. Then in that case, you can use some of the very powerful visualization tools that Avizo offers. For example, you can use the volume rendering module. And for those who are not familiar with volume rendering, that's totally fine. But basically what volume rendering does is it assigns a color and transparency to the intensity values in the data to generate a visualization like this. And that mapping is done through this transfer function, which you can see here. I will not go through the details of this transfer function. I think we might be able to discuss that in a later workshop, or you can also go through the Avizo introductory workshop YouTube video that we provided in the workshop website. But here, for instance, even just using the default color map, you sort of get a sense of the structure in the data, in particular the sand particles. So this is pretty helpful, and let's say I'm now satisfied with my general view or idea of the data set. I will go ahead and start my segmentation. And the way to do that is to first select your data object, and then click this segmentation editor button here on top. So once you click this button, it automatically switches you to the segmentation editor. Here on the top left, you can see the data object that corresponds to the image stack that we are currently segmenting. So this is our input image stack. And here you will find the data object corresponding to the output. So this is basically the label images that we want to generate. And this object has been automatically created once we clicked the segmentation editor button. So if we go back to the project view, you can see actually that we have this new object here, which is the label images. Okay, so let's go back to segmentation editor. And here we have a list of materials that we have in our label field. And by default, Avizo creates an exterior and inside material. So exterior material corresponds to pixels or voxels that are not assigned, and it has the numerical value of 0 within the label images. And all the other materials will have the non-zero values, as we discussed before. And the numerical value of the material just corresponds to the material's index within this list. So this one will be 0, the next one is 1, the next one is 2, 3, 4, and so on. So that's very intuitive. So we can add materials or delete materials here. Locate, for example, once you've segmented something, you can focus on a certain material using locate. For now, let's add another material and rename inside into air. So let's double click the name, type air, and then double click the other material and let's rename it to sand. All right, so when we start the segmentation editor, as I said, the default output label field is generated, and this output label field is initialized to all zeros. So everything is assigned to exterior. So we can actually see that if we click this 3D preview. So this shows us basically the voxels assigned to exterior in this 3D view. Let's just turn that off. And since we're here, I'll talk about the multiple views here. So here you have a 3D view of your selection or your segmentation. And here you have the different 2D view slices along the XY plane, YZ, and XZ. So you can switch to the different slices using the sliders, or type in the slice index here directly if you want. You can also zoom out and zoom in as needed. And as you'll see later, we can interact with these views to perform our selections. And here with our 3D view, we have the same kind of interaction that we can do with the 3D view that we saw before in the project view. All right. And over here on the bottom left, we have our segmentation toolbox. So it consists of a bunch of tools that we can use to create segmentations or selections in Avizo, and we'll go through a couple of them later on. Now, a very important concept when we're doing segmentation is to understand the idea of a selection. So a selection is basically a group of voxels or pixels that are currently selected or highlighted. Okay, and once you have a selection, you can then perform different operations on the selection. So you can, for example, clear the selection, replace, add a selection to a particular material, or subtract a selection from a particular material. Okay? All right, so let's start with a very simple example, starting off with the brush tool here. So let's click the brush tool, and as the name implies, the brush tool allows you to brush directly on any of the slice views to select pixels, right? So let's say I want to add these pixels here to the air material. So I'm gonna make that selection by left clicking and dragging in this region that I'm interested in. And as you can see, the selection that I made gets highlighted on the image view here, And at the same time, it gets highlighted in the 3D view over here. Okay. Again, this is currently just a selection. It has not been assigned to any material yet. So let's say I want to assign this selection to the air material. I have to click on air. So this makes air the active material or the current material. And then I would have to click the add button. All right. So as you can see here on the tooltip, you can also press A or plus to add the selection to the material. And now the selection has been added to the material air. So because this checkbox is checked here, which is for the 2D preview, you can see the air material previewed here on the 2D image views. You can also check this checkbox here, which shows a preview of the material in this 3D viewer. So yeah, so you can toggle these checkboxes here to decide what you want to see on your 3D view and on the image views. Okay, so now let's say I want to add more selection to my air material. And let's say I accidentally brushed inside this sand area, and I want to, let's say, clear this selection. All I have to do is click this clear button or press C. That gets cleared. And let's say somehow I managed to add this selection to the air material. So there's clearly a mistake here, and I want to correct that. What I can do is just brush over here, and I can either say subtract this from the air material, or I can also click on sand and click replace. And what that will do is it will reassign the selection to the new active material and remove it from the original one, which is the air. Okay. So now because I just want to give you guys a quick overview of the whole workflow. For now, I will not go through each of the segmentation tools that we have here, but instead I will focus on the texture classification method here. So right now I won't even go through the details of this tool. We will go through these options later on, but for now I want to give you a general idea of what this texture classification does. So the idea here is that you can use any of the methods. Generally, I would use the brush to create just a few selections and assign a few labels to our materials, as we've done here. So I might want to add a few more. For example, here, this would go to sand, and I will add that. And maybe I would say, okay, this is also air. All right, so basically what I do is initialize the label field with just a very few selections, as you can see here. So it just took us a couple seconds to generate these labels, very easy. And what I can do now is go to texture classification, and I won't even change any of the parameters. I will click compute preview here. So when you click compute preview, you can see here that the slice have been somehow updated. So it kind of shows you what the texture classification algorithm would do, or how it would classify your slice based on the input that you've given it so far. And let's say, okay, I'm not super happy with this. I want this area to be part of sand. So what I can do is go back to the brush and, okay, let's say a brush on this region, here, also here, and add those to sand. Okay, and then let's go back to the texture classification and do compute preview again. So here now I think I'm, let's say for now I'm okay with this kind of result. And as the name implies, this is just a preview on one slice. Once you click on this apply and create a new label field button, what Avizo will do, so let's just do that. What Avizo will do is apply the texture classification to the whole data set, all right, to all the slices. And it will perform this classification based on the initial values that you gave it. Okay, and let's see what Avizo did. So let's say, let's look at the 3D preview of the sand particles. Okay, so that looks pretty decent to me. And then let's say, let's preview the air pockets. So that looks fine. So let's say for now I'm okay with this. So again, I just wanted to show you a quick overview of the whole workflow. We'll get back to this later on and how to refine it. But one thing I quickly wanted to show maybe now is that you also have these two menu options here on top that allows you to apply operations to your whole segmentation data, for example. So filling holes, removing islands, smoothing labels. So let's say, let's just click smooth label. And for example, before we apply the smooth label, take a look at these edges here, which are kind of jagged. And let's say I want to apply the smoothing. So as the name implies, the smoothing smooths out the segmentation. So let's say click apply, and you can see the jagged regions got reduced. So this makes your segmentation smoother. And basically, you can, let's say we can do this again to keep smoothing the data or increase the smoothing neighborhood. Okay, so let's say for now I'm okay with this. Then you also have the selection option here, where if you, for example, currently have a selection active, you can click this selection here and apply some operations to the selection. So again, we'll go through this, through some of these options later. And for now, let's say I'm very happy with this current segmentation result that I got in a matter of a few minutes. By the way, before I move forward, I just wanted to show that you can also go through the slices here to kind of check the segmentation results across slices. And one thing that you would notice, for example, is that there's this region here that was not segmented. And for now, let's say that's fine. As you can probably imagine, the reason why this was not segmented is that the regions that I selected earlier on as examples don't match this region in terms of similarity. Okay, so Avizo intentionally did not select that, and that's fine. Okay, so for now, these will be left to be part of the exterior or not assigned material, and that's totally fine. Okay, so now let's say I'm done with my segmentation work and I'm happy with this. So we can go back to our project view now. And what do you notice here is that there's actually a new data object here, which is the segmentation that the texture classification generated. Okay, So this one here, you can actually see it in the preview, was the input to the texture classification tool, right? So this was our initial segmentation. And then when we used the texture classification, it generated a new one over here, okay? And again, as I said, let's say right now, this is the output that I want. I'm happy with this. So we'll go on to the next step of our workflow, which is 3D reconstruction. Before we do the reconstruction, I just wanted to save the project first, just to be sure that we don't lose any of our work in case, for example, the computer crashes or whatever. So let's just go to File and Save Project. So here we're presented with a bunch of options. So actually we have two options here. So we can either save the project so that Avizo minimizes the size on disk, or we can save the project so that the computations are minimized, and let's say we don't care about the size, so this will generally use more memory on disk. So for now, I mean, let's say I don't care about the disk size, and I'll choose this option. So if we click OK, we can pick a folder and file name for the project. So let me just create a new folder here. Give it a name and hit save. So next, Avizo will ask you what to do with the individual data objects that you have here. And what I would usually do is just click autosave, and that will save all these files in the same folder as the project folder. Otherwise, if you click save, you will have to manually specify where to save these objects. So let's do autosave for now, and that should save our project. And if you look at this folder, you'll see the project file here and the individual data objects that we have here. Okay, so later on, even when we close Avizo here, you can just go to this folder, double-click this project file, and it will get you back to the state where you were at the point where you saved the project. Another thing that I wanted to do before we do the reconstruction is to just clear up our viewer here. And what I'll do is I wanted to turn off the volume rendering. And to do that, you just click the sort of square part of the icon in the project view. And you can do that for any display module, basically, to switch them on and off, as you can see here. And let me just reset the view here. Okay, so at this point, we have our label images. And if you recall, in our workflow, the next step is to generate a 3D model using the reconstruction step. And in Avizo, this is actually very easy to do. All you have to do is use a generate surface module. So as you can see, this one says reconstructs 3D surface models from a labeled image. And that's exactly what we want to do. So let's create the module. And for now, we will keep the default settings. But later on, we're going to dive deeper into this module to see what else we can do. But for now, this is fine. And if we click apply, Avizo will generate the 3D model for us. And that's it. As you can see, it's really very easy. This is actually one of the easier steps in the workflow. And if you click on the surface object, so this is the 3D model, essentially. So you can see some of the properties, like the number of points or vertices and the number of faces or triangles in the model. And in order to visualize this 3D model, we can attach a surface view. So let's do that right now. Okay, and it looks a bit weird right now, but if you look around, that is a 3D model, and what we're seeing right now is essentially like the exterior part of the surface, and you can see this hole here. If you remember the part that wasn't segmented earlier, that's this hole. And now let's say you want to only see, let's say, just the mesh for the sand particles. What you can do is to first clear the buffer of the surface view. So you can think of the buffer as the collection of triangles that you want to see in the surface view. And right now I will want to clear the buffer, so I click the clear button and then remove. So this removes all the triangles in the buffer, and thus as you can see here, we don't see anything in the surface view, right? And now what I want to do is select some triangles from our mesh and add them to the buffer. And here the way you select triangles is by specifying two materials, so one here on the left and one on the right, and all the triangles that are in between these two materials get selected. Okay, so let's say I want to pick the triangles between the sand material and everything else. So you see here they get highlighted. Okay, this is essentially the triangles around the sand material, right? So for instance, I just want to see the triangles that are between the sand material and the exterior. So you can see the triangles here that are in between these two materials. So exterior here includes the outside or the boundary of our object, and also the exterior material in our labels. Okay, so for now, let's say I want to see all the triangles for the sand material. So as you can see here, those triangles are highlighted in the viewer, and once we click add, they essentially get added to the buffer, and now they're displayed here in our surface view. And now you can do your further analysis if you want. So you can extract this mesh. We'll look into that a bit later. And then you can perform your quantitative analysis on this mesh. And you can also export it to, so you can use it on different applications if you want. All right, so for now, let me just again clear the buffer, and this time let's take a look at the air material. So let's again click add, and now you see the mesh for the air material. So the other thing that I just wanted to quickly show are some options for showing the surface or the mesh. So you can have this default shaded view. You can also have outlined. So this shows you the mesh plus the triangles. You can also just see the triangle lines, essentially, some point-based representation, and a transparent rendering of the surface, which could be nice. For example, if you want to take a screenshot that shows you sort of an overview of the whole mesh. So let's just go back to our default shaded representation or view. And the last thing that I wanted to show was if you go here to more options, there's a bunch of, let's say, more detailed options for the shading. We won't go through all of them, but one thing that I wanted to point out are these three options. So here you can basically select um, which faces, okay, of the triangles you want to render. And currently it's set to both faces. And now you can just say, let's say front face, okay? And you see basically a smaller subset of the triangles. And if you click back face, it's again a different subset. And this is important because, as you'll see later on, once you export this 3D model and use it on, let's say, external mesh renderers, the best way to view your mesh is usually to render both faces, okay? Because if, for instance, your renderer by default does not render back faces for optimization purposes, so you'll see something like this, which might look weird depending on your object. So just keep that in mind, and we'll get back to that later on in the workshop. Okay. So at this point, I'm not sure if you noticed, but we have already been performing the visualization and interaction with our 3D model, which is the last step in our workflow, if you remember. I mean, there's other ways to visualize our model, but for now, what I want to do is go to the next stage or next level of visualization, which is visualizing and interacting with our model in virtual reality. Okay, so now let's just save our project so that we have a backup. And also, if you are working on your computer using Avizo, saving the project would now allow us to bring our project and essentially our data sets into any of the VisLabs VR facility that is available for you. So you can save your project and data sets in or on an external hard drive, or in the cloud, or in any of KAUST's network-based storage like DataWaha, so that you can access your project from the VisLabs VR facilities. And using the VisLabs VR facilities allow you to use Avizo directly in virtual reality with just a few simple steps that I will show in a little bit, and more importantly, without doing any additional coding. Okay, so I now switched to our VR workstation located in the showcase area. So as I've mentioned before, the showcase area is located in building 1, level 2. And when you pass by building 1 along the spine, it's the area with the big screens, right? With the nice visualizations on display. And our VR workstation is located in the same space. And you will see it. It's one of the PCs with Avizo, and it also has virtual reality headset. In this case, we have an HTC Vive for VR. Okay, so now I started Avizo on the machine, and I actually copied the project that we generated from my computer, this sand project file. So as I said, you can copy your project and data sets locally to this computer, bring your external hard drive, or access your data set and project through the network. So I have the project and files here, but I decided that I wanted to show you the whole workflow again, just to emphasize the how easy and quick it is to do the whole workflow if you're working with relatively simple data sets like this one. So this time we'll do the whole workflow without talking about the basics of Avizo. Okay, so let's go ahead and open our data set, right? And I'll go directly to the segmentation editor. Okay, and I'll create our materials. Okay, and now get some samples for air. So I click Control Z there just to undo my selection. So we can do that. All right, so let's say I'm okay with this for air. Now for sand. So notice that I'm also trying to get some samples along the edges of the objects. So this would be really helpful for the texture classification. Okay, so let's say I'm okay with this. Let's see. All right, so this actually looks really nice. Let's now apply the classification to the whole data set. Okay, so this looks fine to me. So let's just do a little bit of smoothing here. All right, let's increase the smoothing radius. All right, so let's say this looks really good to me. Let's go to project again. Now we have our segmentation here. So let's do the reconstruction with the default settings. Okay, now we have our surface. So we actually can click here, or we have the suggested objects here. All right, so this is now our surface view. And as you can see, it took us just a few minutes to get to a decent result here. So let's have a look at the sand. Right, so that doesn't look so bad. And let's just turn off the ortho slice. Okay, so now we did the whole workflow from segmentation to reconstruction to visualization on the desktop. And now I wanted to show you how easy it is to view our model in virtual reality using Avizo. Okay, so for that, we're going to use an additional application called TechViz, which will serve as our bridge between Avizo and our virtual reality system. Okay, so let's go ahead and create an object here in the project view. So create object. So you can just search for TechViz connection. So TechViz connection module, and let's create that one. And now let's run TechViz, which, as I said, is an external application. So you can also just search for it here. So TechViz controller, let's go ahead and start that. All right. And now let's establish the connection between TechViz and Avizo by clicking here in this VR icon and clicking on the Avizo window. Then let's go to the TechViz connection module and click connect. Then we can also do auto scale to automatically scale our model in VR. And now you should see your model in Avizo. Okay. All right. So, okay, let me actually start the VR view on the desktop so you can see what I can see. So you can see the controllers there. So you can see them moving if I move them here. And let me also just click center here. So this center button puts the model in front of you in VR. All right, so I'll keep this window open so you can see what I can see in VR. Okay. So let me just grab the controllers here so you can see I have the controllers
and sort of my virtual hands visible here in the virtual world. So I'll move back a little bit just to get rid of the grid lines that you can see here. So the grid lines here sort of help you stay within your virtual reality play area to keep you safe from like bumping into objects around you. And you have to initialize this in VR when you set up your VR environment. Okay, so let's just move back a little bit to get rid of that line. And I'll stay seated for this example, but you can of course stand up and move around. So here I'm interacting with my 3D model. So you can click the grab button. So click and hold to sort of virtually grab the model and move it around, move closer to it, put it farther from you. And you can open the Avizo window by double clicking the trigger button. Okay, so as you can see, the menu sort of moves around with the object. So if you kind of lose track of where it is, you can just double click again and it will show up to your right. Okay, and what you can do here with the menu is let's say click modules, and this will show you the modules that are currently open in Avizo, so you can interact with them. So let's say I want to click the surface view. So it will give me some of the options that I can change in VR. So take note that not all of the options are available in VR. And so yeah, if you want to change some of the settings, you probably have to change them from the desktop. But there's a pretty decent number of options that you can change in VR. So for example, we can change the materials, we can change the color coding. So let's for example switch to the air material. So what we can do is first click all and remove, and now let's click the air and add. Okay, so now we can see here the air material. Okay, so the color coding might look weird, so we can switch the colors to let's say constant. Okay, so this assigns a constant color to the whole material. Okay, all right. So okay, now let me just let's clear again and switch back to the sand. So let's add. Okay, so as you can see, it's pretty easy to switch back and forth between your materials. And yeah, we were in VR in just a matter of a few minutes, and you can do these cool things where you can peek inside your model. And this is also in stereo, right? So you really have a sense of the 3D shape of your model. Okay. All right. So just another thing that I wanted to mention, if you look here at the TechViz controller window, you will see some green icons here. And these actually correspond to your headset and two controllers. So if these icons turn gray, that means either your headset or controllers are not being detected by TechViz at the moment. And that typically is because the headset or controllers are not visible to the trackers or base stations that we have here. So you just you can try to move them around, lift them up and wave them around so that they become visible again. Okay, and that was it for visualizing your data within Avizo and using virtual reality. And if you forget these steps for setting up Avizo with VR, we actually have the instructions in the wiki. So if you just go to the wiki of KVL, you can go to resources, and we have this Avizo with VR page, and we have this short step-by-step guide on how to run Avizo with VR. And this is essentially what we did just a few minutes ago.
Yeah, so that was the first part of our workshop today, which is the overview plus Avizo basics. So hopefully by now you have a general idea of what the whole workflow is. So later on, as I said, we'll go and dive deeper into each of the steps. And yeah, if there's any questions, you can post them on the chat. And I just wanted to point out one question that was posted earlier. So unfortunately, Mac OS or the Mac OS version of Avizo is no longer supported. So we recommend using Windows or Linux OS. Okay, so if you have any questions, you can post them on the chat. If not, then we're going to go for a 3-minute break. And yeah, seems like there's no questions. So yeah, let's go for a 3-minute break, and we'll see you guys back here in 3 minutes. All right, so we're back into the workshop. And for the next part, we're going to go and dive deeper into the segmentation tools in Avizo. And as usual, if you have any questions, feel free to post them in the chat. Let's now take a closer look at the image segmentation step in our workflow. Again, the goal of image segmentation is to generate label images from our input image stack. And so far, we've seen how to use Avizo to generate label images, in particular using manual selection using the brush, in combination with texture classification, which is some form of machine learning. In the next few minutes, I will show you how to use the other segmentation techniques or algorithms in Avizo, such as thresholding and Watershed, just to name a few. In addition, I will also discuss some pre-processing options in Avizo. Pre-processing is applied to the input image stack in order to reduce artifacts, such as noise, or enhance features, such as edges, in order to help improve the results of some segmentation algorithms. Later on, I will show you some examples of how to use pre-processing to improve segmentation. Later on, I will also talk about Ilastik, which is an open source application that is widely used in the research community for performing image segmentation. So we can use Ilastik as an alternative to Avizo. Let's say once you've exhausted all the segmentation methods using Avizo and still not satisfied with the results. So then you can use Ilastik as an alternative to try and get better results. So the other thing that I just wanted to mention here is that image segmentation would typically be the most complex step in our workflow, especially if you're dealing with very sophisticated data. And the other thing is that usually it would take some trial and error to get good results. Even if you're dealing with, let's say, a simple data set, it might take a few tries to get a good combination of pre-processing steps and segmentation techniques. But the good thing is, once you've figured out a good combination or a good workflow that works for your data set, you can then just reuse that workflow once you get new scans of similar objects or similar materials in your data. Now let's switch back to Avizo and have a closer look at the segmentation tools that it has to offer. So first, let's open a dataset. And for now, I will open the SandCT dataset and keep the default options here. So I wanted to start with a simple dataset so we can focus on learning the segmentation tools. But later on, we're going to have a look at more complex datasets. Okay, so let's go ahead and start the segmentation editor. And let's create the air and sand materials. All right. And we've already seen the brush tool from earlier examples. And if you can remember, the brush tool is our way of making manual selections in our data set, so we can click and drag in the slice views to create selections. So the other thing I wanted to mention is if you press and hold the control button while making selections, it switches to an eraser, as you can see here. Okay, so the other thing I wanted to mention is you can use this slider here to change the size of your brush. You can also press and hold control and use the mouse wheel button to change the size. You also have these predefined sizes here, so that's very useful. You can also change your brush to a square brush, as you can see here, which is useful if you have structures in the data that are more straight and has corners. Okay, but let's keep the circle for now. There's also an option here to specify a mask. So if you enable this, you can specify an intensity range on which the brush will only apply on. Okay, so for example, here you can see the pixels that are highlighted in blue, and your brush will only get applied to these pixels, as you can see here. Okay, so let's disable this again and clear our selection. So the next thing I wanted to show is the Lasso tool here. And what the Lasso tool allows you to do is to draw contours in 2D, like this one. So you can left click and drag to draw a contour, and all the pixels inside the contour get selected. So you can, for instance, add them to your material. So you can also use some predefined shapes, such as the ellipse and a rectangle to create selections. And you can also specify a contour in 3D. And this can be a bit tricky, so the first thing I like to do is to show a volume rendering of the external material here. And so let's just adjust the transfer function so we can see more. And when you use the Lasso tool in 3D, you would specify a contour like this. And this 2D contour gets projected towards the back. And if you look, what happens is everything in the back of that contour gets selected. So this can be a bit tricky to use. And what I like to do is usually isolate the region that I want to select, like this one, if you can, and then draw the contour in there. So click the Lasso tool again and draw the contour like this. And don't forget to click the trackball here if you want to move around, because otherwise clicking in the 3D view will draw a contour again. So let's just add this to our sand material. And all right, let's move on to the next tool. But before we do that, let's just turn off volume rendering here. And let's clear everything. So we start from a clean slate. Now let's take a look at the next tool, which is the magic wand. So if we click here, you can see that some of the pixels here are highlighted in blue, And those pixels are the pixels with values that are within this masking range. So um, the magic wand tool basically performs a region growing selection based on a seed point that you specify. So for example, I can click here, left click, and that creates a seed point at this point. And what the magic wand does is it takes a look at the neighboring pixels starting from this seed point and selects everything that is connected together that are within this um, range that you can see here. So for instance, you can change the range that you're interested in. So you see the highlighted regions change. And let's say I specify a different region, let's say over here. Okay, so that selects the connected regions over there. And let's look for a more interesting example. So let's say here that I see there's this region here with high intensity pixel values. And what I can do is click here, and this selects the region there. So let's clear our selection first and redo that so that we only get the region here. And so right now it just selects the pixels from one slice with the high intensity values and are connected. But if I click the all slices option, this now gets grown into the region outside the slice and across multiple slices. And in this case, let's say I don't want this region over here. You can, for instance, adjust the intensity range, and then your selection gets limited to this area here with the really high intensity valued pixels. Okay, so that's the magic wand right there. And again, let me just clear our selection before we go to the next tool. So the next tool is the propagating contour. So the propagating contour allows you to specify multiple seed points in your image slices. Okay. And what it does is, if you click initialize and then move this time slider to the right, it starts to perform region growing starting from the seed points that you created, as you can see here. And right now it's doing this region growing in 3D. So it's doing it across all slices. And you can change the settings here to do it only by slices. And the other options that you can specify are edge sensitivity and image intensity weight. So these parameters correspond to how strict the region growing is in terms of considering edges. For example, edges that you can see here. So the higher your edge sensitivity, let's say the highest is 1, the slower the region will grow along the edges. So it will try not to cross the edges. And vice versa, if the edge sensitivity is very low, let's say 0 or 0.1, the region growing will just go across the edges quite easily. And it's quite similar to the image intensity weight. So it's actually very similar. So for example, if you're in a region without edges necessarily, like the region here, the image intensity weight also specifies sort of how fast the region will grow in these areas without edges based on the differences in intensity values within the region. Okay, so by default it's 0.5 and 0.5 here. So let's just see how that looks like here again. So let's keep growing the regions, right? So you can see at some point it starts to overflow through the or over the edges at let's say time 6. Okay, and so we can, let's say, move back and pick this if we want. Now let's say I want to clear my seed points again and clear this. Then let's create some new seed points and try this with a different setting. So let's say now I'm gonna lower these two and initialize. Okay. Right now let's try this again. And okay, as you can see here, the algorithm is basically less strict in terms of respecting the edges and intensity changes. So as you can see, I'm just on sort of even less than the time step from before, and I've already gone past the edges over here. Okay, so again, this is one of the things that you have to gain an intuition of, and just try playing around with the values and trying different things. Okay, so let's go back to the 0.5 parameters, and you can see the regions here are smaller, and you have to move further in time to just get to the edges. Okay. All right. So just in summary, or sort of just to give you a better intuition here, again, the values here sort of control how fast the region here is growing through time, and in general also controls how much the region growing respects the edges and changes in intensity values. Okay, so again, let's clear up our selection here and our seed points, and move on to the next segmentation tool, which is the blow tool right here. And the blow tool is similar to the other region growing tools that we've seen before. And to use the blow tool, you first click on your slice to specify the starting seed point, and slowly move your cursor away from the point while holding the left mouse button. And as you move further away from the starting seed point, your region starts growing. And once you release your left mouse button, all the pixels inside the contour of your region gets selected, as you can see here. And just like the other region growing techniques that we've seen before, the blow tool tries to consider the edges in the data, and it tries to avoid going over the edges. And this parameter can be specified using the tolerance value here. So let's say we set this value to a very low value of 1. Then you basically get more strict in terms of respecting the edges. As you can see here, I'm moving far away from the initial seed point already, but the region is not growing as much as before. Okay, so it's more strict in terms of crossing the edges. So even low intensity changes, or let's say lower magnitude edges would block the region growing. And the other way around, if I try to put in a high value for tolerance, the region grows faster and goes across the edges faster, as you can see here. Okay, so again, it's a matter of figuring out the correct value depending on your images. And the other parameter that you can specify is this Gauss width parameter here, which sort of controls the amount of smoothing that is performed or applied to your images. So what happens is that under the hood, the images here, or our images in our image stack, gets automatically smoothed with a Gaussian smoothing filter. And we'll talk a bit more about Gaussian smoothing later on. But for this particular parameter here, you can set it to a low value of 1 and a maximum value of 8, with 8 giving you the most smoothing. So what that does is, you don't see it here, but the edges actually are sort of smoothed out, and they slowly disappear with higher Gaussian width here. So you can see here that the region is growing even more faster than before. Okay, and even if we, let's say, set this to let's say 30, yeah, the region is still growing pretty fast. But if we lower this value to, let's say, 1, yeah, so the region grows much slower, because under the hood, the image is not smoothed out as much. Okay, so again, this is so these parameters take a bit of time to get used to get a good intuition, so that you can easily set them according to the requirements of your image data. Okay, so for now, let's again clear our selection and move on to the next tool. And the next tool is called the threshold. Okay, and it's probably one of the most commonly used segmentation tools, or at least it's one of the easiest to understand and to use. And what the thresholding tool does is it selects all the pixels that are within a minimum and maximum range that we have here on the bottom. So you have a minimum intensity value and a maximum intensity value that you specify, so you can change that dynamically. And all the pixels within this range can be selected. So for example, here they're highlighted in the image slices here, and to select them you can just click this button here. Okay, so you get your selection pretty quickly, but as you can see in this particular example, because the data set is noisy to begin with, you can see that we have these sort of outlier selections over here, and I'm not sure if you can see it clearly, but those correspond to these spots over here, right? And that's because of the noise in our data set. And in just a few moments, we're going to try to deal with this using pre-processing. Okay, so before we do that, I want to first add this preliminary selection to air. Okay, let's add that. And then let's try to get the sand material selected. So let's go to sand again, and then let's use this maximum over here. Just copy, Control-C, paste it here, and then move this all the way to the end to select now the sand material. So the other thing that I just wanted to mention in the thresholding tool, and in actually some other tools in Avizo, is that you see this sort of this tool here where we can specify the minimum and maximum values. Right behind it, you can see a sort of grayscale plot, and this is actually the histogram of our data set. Okay, so the histogram roughly tells you how many pixels or voxels in the data has a certain intensity value. And in this particular data set, you can see that there's sort of these two peaks over here, corresponding to the low intensity pixels here for the air particles or air pockets, and the higher intensity values here corresponding to the sand particles. That's why if we roughly place our cursor here for specifying the minimum value and set the maximum value here, we get to select the sand particles, as you can see here. And for now, let's again make the selection here. And just like before, you can see these small selections here that we don't really want to have there. And it's just caused by having a noise in our data. Okay, and for now, let's just add the selection here. Okay, so we now have our sand material and our air material, but with the noise in the selection, as I've mentioned before. And in this particular case, I know that my data set has noise, right? And that noise is causing these unwanted selections over here, and it makes my thresholding tool give me, let's say, not the best results that I can get. And this is where pre-processing can come in, right? So because I know that my data set has noise, then I can, let's say, decide that maybe I can do some step before segmentation to try to get rid of the noise over here. Now, it's a different story if these tiny particles over here actually correspond to parts of the data or object that you're interested in, right? So maybe these are actually tiny air pockets inside the sand grains, right? And so you know more about your data, so you should be able to make that judgment call. And in our case, in this particular example, we know that this is noise, so we'll go ahead and try to get rid of it to try and make the thresholding results much better. So let's go ahead and go back to our project view. And as you can see, we have here our segmentation with the noise over here. You can see it in the preview. And what we want to do now is apply pre-processing, okay, to our input image. And when I say pre-processing, in our case, since we're dealing with image stacks, a typical module that we want to use are image filters, right? So if you just type filter over here, you're gonna see a bunch of filters. So this is a lot of filters that you can apply to your image stack. So let me start with one of the simplest filters that you can have, which is the box filter. So let's go ahead and click box filter, and it gets created here, attached to our input image stack. And just like before, if there's a module that you're not very familiar with, you can click the question mark button here to get a description of the module. And for the box filter in particular, it's actually very simple. It performs an averaging operation on a neighborhood of pixels. And the neighborhood size can be specified here with the kernel size along X and along Y. And the auto scale here just specifies what value gets assigned to K here. So usually you would want to specify this to yes, so that the box filter actually results in averaging. Because if you set this to no, then the box filter will be equivalent to just summing up the pixel values. Okay, So let's close this now. Box filter, and let's say we want to apply the filter in 2D, okay, across slices, and let's keep the default values of 3 by 3 sized boxes for averaging, and hit apply. And what that does is it generates a new image over here, or a new image stack, and let's have a look at how it looks like. So actually gets overlaid over here, but let's have two windows over here to see the two images side by side. So we have, let's put on the left the original image, and on the right the filtered image. And as you can see, the image on the right is slightly blurrier because of the averaging that we did. And we can of course change the parameters here. Let's say let's just exaggerate and use a bigger pixel neighborhood for the filter, and hit apply. And as you can see here, the resulting image stack is just much blurrier. So of course you don't see the noise anymore, but the edges get sort of diluted, right? Or they start to disappear and get smoothed out. And this is one of the trade-offs that you have to take care of when you're applying filters to your image stack. So our goal is to reduce the noise, but at the same time, we want to keep the important features such as the edges. And yeah, so this usually takes some trial and error, and getting used to the different filters, and getting familiar with the filters, what they do, what the parameters do. And at some point you get a good intuition of what these filters do, so you can better decide what filter to use with your data sets. So the other thing that I just wanted to show is there's actually a really nice way to try out different filters pretty quickly. Okay, so let's just go back to our single window view, and let me just delete these here. Okay, so there's actually what's called a filter sandbox, as you can see here. So you can also type filter sandbox here. Okay, so what this filter sandbox does is it allows you to try many different filters and filter settings pretty quickly. And you have this region here that's enclosed in this box, and you can adjust the size and position of this region. And what happens is, if I now click filter sandbox, and here in the properties window, if I pick one of the filters here, let's say box again, and same parameters as we had before, it automatically applies the filter onto the region over here. So you can sort of have a side-by-side comparison between the filtered region and the non-filtered region. And you can move it around dynamically like this to sort of inspect what's going to happen if I apply the filter to a region of the image. And so this is the box filter, and of course you can try other filters such as bilateral filter. So let's just change the parameters, for example. Okay, so you can just keep trying different parameters. So this might look sufficient for you. Again, it depends on your data set and use case scenario. And let's say I want to try a different filter, let's say the median filter. Okay, and here let's say I want to apply the median filter in 3D. So we can click 3D and a neighborhood of 26 with 3 iterations. And this actually looks pretty good to me as well. So you can see that the noise is gone, but the edges are still more or less there. And yeah, so there's quite a lot of filters that you can try here. And you can try out the different parameters as well. So for now, let's say that I'm happy with the median filter, or let's say I just want to quickly try using the median filter. So then you can go ahead and go back here and create a median filter object. And we can disable this filter sandbox and go ahead and go to median filter and put in the parameter that we had before that we think would work well. Hit apply to apply the filter to our whole image stack. And now we have this new image stack that's been pre-processed, right? So now we can go ahead and see if our thresholding would actually be improved. So we can either modify the segmentation that we had before, or we can create a new label field. So let's just accept the default one. So we can start from scratch. Okay. So let's just again create the materials here. Okay. Let's just reset the view. And as you can see here, if you look at the slice views that we have, we don't have the noise anymore, but the image is slightly blurred, right, because of the filtering that we did, but we still have the edges in the images, which is really good. Okay, and this time let's try and see what the thresholding does. And as soon as I click the thresholding, Avizo actually automatically selects a minimum and maximum range that it thinks I would like. And this time it's actually correct. And I hope you notice the big difference this time, where because we don't have the noise, the initial selection is already very, very good, as you can see here. And you'll see that more when we click select masked voxels. So now if you look at the 3D selection, you can see that there's really no unwanted like selections, you know, like that's coming from the noise, as you can see here. So this is really, really nice. And let's say I'm very happy with this, and I'll add that to sand. And now let's just try to label the air particles. Okay, and then select and add. Okay, so as you can see, this is a proof or a really good example of where pre-processing really helps the segmentation techniques quite a lot. Okay. The next thing I wanted to show is the segmentation tool called Watershed. And for this segmentation tool, I wanted to open up a new data set, which is a CT scan of a plastic bottle with cap. And this data set is available from Thermo Fisher's tutorial that shows a similar example, so showing the Watershed algorithm to segment the data set. And I will provide the link to that tutorial in the workshop website if you're interested in having a look. So as usual, what we would do initially is to have a look at the data to get a general feeling of the data set that we're dealing with. So using the ortho slice, we can sort of see the general shape, but in this case, it might be helpful to have a look at the volume rendering of the data set. And we can turn off the ortho slice. And as you can see here, this now looks familiar to you probably. So you can see the cap over here and the plastic bottle. And our task for this example is to separate the cap from the bottle using segmentation. Okay, so let's go ahead and start the segmentation tool. And as I said, I wanted to use the Watershed segmentation tool for this example. And you can probably read the tooltip here, but the general idea for the Watershed algorithm is that we provide markers in the data for each of the materials, and at each of the marker points in the image, you can imagine that we flood the image with, let's say, water that corresponds to the material, and the point where the liquids for different materials meet are what's called watershed lines, and these watershed lines allow us to separate the different materials from each other. So this might not make sense at all for now. That's why I wanted to first demonstrate how it works, and then later on explain in more detail what's going on. Okay, so first let's create our materials: cap, bottle, and air. Okay, so as I said, we have to provide markers to the Watershed algorithm, and to do that, we use or we can use the brush. Okay, so let's get some samples for the cap first. So let's just adjust the radius here. Okay, so let's make so let's brush around. So I just undo that over there. Okay, so let's just make a few brush strokes here, and let's add that to the cap material. Then let's do the same for the bottle. Okay, just a few brush strokes here. Maybe we can also do some here, right? And let's say we add that, and then do the same for air. So just brush a little bit here. Okay, and add. Okay, and so now that we have some markers for the different materials, we can go to the Watershed tool. And first thing we have to do is create a new gradient image. Again, I'll talk more about what this is used for later on, but for now, let's go ahead and do that. And then just click select all materials. So we want to perform segmentation for all the materials. And for now, let's click side by side here. I'll go back to these options later on and click apply. Okay, so this will create a new label field object, as you will see later. So this might take a few seconds. Okay, so this is the result of the Watershed algorithm, and it's pretty decent. So if you just look at the slice views here, it looks correct. There's a subtle issue here where you can see the black area here that's supposed to be air is mislabeled as the cap. So we can fix this later on, but for now what I want to do is explain what just happened with the watershed, okay? And in order to explain that, I want to go back to the project view, and keep in mind that before we ran the watershed algorithm, we generated a gradient image called gradient bottle, okay? So let's go to the project view, and we'll actually see the gradient bottle over here. And I wanted to show you that. So let's just turn off the volume rendering here and attach an ortho slice to the gradient bottle. So the gradient of an image basically shows you the strength of the edges, right? So how different the two values are across an edge in the image. And this is, for example, the gradient image for slice 165. And let's take a look at slice 165. Okay, so let's just turn this off, this on. So you can see that here. So just to see the gradient image better on top of the actual image, we can use a height map slice, which you can see here. And let me just put an offset to it. So the height map slice displays an image as a height map, and the higher the intensity value, the higher the height map goes, as you can see here. And as you can see, the gradient image creates this sort of wall-like structure along the edges. And what the watershed algorithm does is you can imagine that if we have markers for the bottle over here, so imagine you have markers here, you have markers for the air material here, and markers for the cap over here, and again markers over here and here for the air. And imagine that these markers become fluid sources. Let's say water starts flowing out of these markers, and the water is somehow, let's say, color-coded according to the material they belong to. And you just keep flooding this landscape over here until the water that corresponds to the material at some point will overflow. Okay, they will overflow and try to cross over this wall. And once the water from two different materials meet on top of this wall, then the meeting, or the line, or the region where those two materials meet, is what we call the watershed line. And we can use the watershed line then to separate the two materials, and therefore segmenting the two materials. Okay, so that's sort of the general idea for the watershed algorithm. And again, it can be tricky to understand, but that's okay. You can go back to this later on, or go and check out the other tutorials online from Avizo. And again, I will provide the link in the workshop website to the other tutorial. Okay, so now let's go back to our segmentation editor and try to fix the error that I was talking about before. So again, this is the error that we want to fix. And this is actually coming from the problem that we actually provided a very limited number of markers in our initial segmentation, as you can see here. Okay, so if you look at the markers where we have air, it's just here and here. So these are actually sort of separated from the region. So if you imagine a connected region that you can grow from these markers, this part will be excluded. So an easy solution to this is to add markers in these two regions here. Or the other thing you can do is just use thresholding to generate lots of markers for the air material. Okay, so let's just try to zoom in here a little bit. Okay, so to make sure that we sort of have at least a few pixels over there. Okay, and then add this to our air material. And now we can again run the watershed algorithm, this time with more markers for air. Okay, so let's go ahead and do that. And before I actually do that, I just wanted to quickly comment on these two options here. So if you choose the option side by side, or let's say if you choose the option separated, the watershed algorithm would actually use the watershed line as the point where to separate the two materials, and you could have exterior materials in between the two materials. While if you choose the side-by-side option, a post-processing step will be performed to fill in the gap in between the materials. So let's have a look at the separated option first and see what it does. Okay, so here we're given a warning that we did not specify, or we did not create a new gradient image to use as the gradient image for the watershed algorithm. So let's go ahead and create that. Okay. So we could also we could have just reused the gradient image that we had before. Okay. All right. So now Avizo actually went ahead and applied the watershed algorithm. Or let's just have a look. Oh, actually no. It what happened there? Okay. For some reason, it switched to the result from before. So anyway, this should be the... Okay, so for some reason I probably forgot to add the thresholded air samples before to the air material, so let's just do that. Okay, something's... Oh, I forgot to click select, right, and then add. Okay, let's redo the steps. Okay, so now we have our gradient image here, and let's choose the separated option. So let's click apply and wait for the result. Okay, so this is the result of the watershed algorithm, and now the air region here has actually been labeled correctly, and this is how the result looks like if you choose the separated option. So if you just zoom in a bit more, so you can see, or I'm not sure if you noticed, but there's actually a gap between the two materials here, between the cap and the air. But if you choose side by side, you're going to see that, yeah, so there's no gap, as you can see here. And for this example, I prefer the no gap result. And you can have a preview here of the results. So you have the bottle here, nicely segmented, and also the cap. So if you don't need the label field for the air, you can also just delete it at this point. Okay, and If you want to now visualize your segmentation as a 3D model, you can go ahead and use the generate surface module that we used before. So again, let's keep the default here. So you'll get a warning sometimes that the data can be too big, but for now, let's say this is fine. Okay, so now we have our 3D model here, and let's take a look at the surface view. Let me just turn off the other modules here. Okay, so this is now the 3D model of our segmented cap and water bottle. And just like before, we can choose to just see one or the other. Okay, so now let's say I just want to see the 3D model of the water bottle. The next tool that I wanted to talk about is the texture classification tool. And for this, we're going to use a different data set, which is the heart muscle SEM. So this is a biological tissue from the heart of a mouse sample. And this data set is from a tutorial by Avizo. So I will provide the link for this tutorial where you can also find the reference for this data set. And again, we can just have a quick look at our data set using the orthoslice and also volume rendering. So as you can see here, this particular data set is more complex than our previous examples. So here the structures are more sophisticated, and also let's say the intensity values are not sufficient to specify thresholding to separate the materials. And this is where the texture classification tool can be really helpful to try. So let's go ahead and start the segmentation editor. And let's start with creating the materials. Just a disclaimer here, I'm not a biologist, so I'm not an expert in terms of the structures that you actually see here in this particular sample. And my basis is the tutorial given by Avizo, so I will try to follow that. And again, you can also go to the Avizo tutorial for more detailed explanations of the structures. Okay, so this is the texture classification tool over here that we will look into next. And before we actually use it, I just wanted to quickly go to the documentation to give you a general idea of what's going on. All right, so here in the documentation, let me just zoom in a little bit. All right, it says there are 3 steps in the texture classification workflow. So the first one is the selection of texture features considered in the model. So what this means is that we have to create initial segmentation or initial labels for our materials, as you can see here. So if this whole image is your data set, you have to create initial labels for each material. So in this case, let's say we have 4 materials over here. So that's the initial step. And the second step is the learning of a texture model on representative annotated training data. So this is the training data that we create in the beginning, and basically the classification tool learns a model for classifying the other pixels in our data. So here we don't really do anything there, but our job is to specify the parameters for this learning process. And we'll talk more about the parameters later on. And the final step is the application of the model to segment a new image, or basically apply the classification model to the pixels that we didn't label. All right. So just another quick description of the algorithm. So the idea is that based on these inputs that we specified, the learning process basically looks at pixel neighborhoods, okay, pixel neighborhoods, and computes numerical features, okay, based on the pixels around the neighborhood. So these can be statistical features or features that sort of describe the pixel patterns, like these vertical lines over here, or these patterns over here. So it computes these numerical features and tries to learn which of these features are the most helpful in terms of discriminating the different materials in our data. So in this example, if you just use a regular thresholding, you'll get something like this. But if you use the texture-based classification, you get something better over here. So each color corresponds to one classified material. All right. So later on, you can go ahead and take a closer look at the documentation to learn more about the different parameters that you can change. But for now, let's go ahead and try it out ourselves. So the first step is to create the initial segmentation. So we'll go ahead and use the brush to do that. So let's just take some sparse samples over here for the mitochondria, and then for this material here. So the idea here is that you don't have to create a lot of input, so this would save you a lot of time. Okay, so let me just make my brush size smaller for this one. All right, let's add that. And now we can go ahead, go to the texture classification tool. So yeah, so the features that are used by the learning method are based on the checkboxes here on top. So the first order statistics are statistical features such as the average or standard deviation of the pixel intensity values within the pixel neighborhood. So the pixel neighborhood size can be specified here. So this is the radius. Then the histogram statistics are basically based on the distribution of the intensity values within the neighborhood. And then you have these co-occurrence features that are more suitable if you have patterns in your data that are like vertical patterns, horizontal, so more directional patterns. And the rotation invariant co-occurrence sort of computes statistical features based on these directional patterns. So for now, because our data set doesn't really have those kind of patterns, I will keep the default options here. And as I mentioned, this is the radius of the pixel neighborhood. Okay, so you'll see kind of a preview here. So this is the size of the neighborhood on which features get computed on. This is the texton size that's used for computing the co-occurrence. So feature rejection is a pattern, or is a feature or a parameter that you can specify to decide or to prioritize the features that are computed. So if you, for example, set this to the maximum of 100, basically you're saying, okay, use all the features that you have for classification. And that could be a bad thing, because what you want to do is sort of say, okay, I want to pick the top X% of these features that are the most discriminative. Okay, so the most helpful in classifying my materials. So you can adjust it later on. And then you have the uncertainty threshold, where this basically says Okay, if you're not sure about classifying a pixel, just leave it as it is. So leave it to the unassigned material. Okay, so you can increase the uncertainty to be less strict about this. But for now, we can keep the default and see what happens. So we have the compute preview button here. And when you click that, you basically get a preview of the classification result on the currently active XY slice, as you can see here. And you can interactively change the parameters here to get a preview of the result here by checking auto compute. So now let's say that, all right, this region here is getting wrongly classified, and maybe also this one here. Maybe let's try to adjust the radius. Okay. So, all right, so this was correcting the issue. So the radius is a very critical actually when you're doing this texture classification, because it kind of decides how big the features are that you want to base your classification on. So this is one of the things that I would usually adjust first. And now this looks quite okay for me. And keep in mind that you don't have to classify the whole image, because later on we can apply post-processing, such as a Watershed, to complete the whole segmentation. So let's say for now that I'm happy with this result. So we'll go ahead and click apply. So this will apply the classification to the whole data set. And this might take a couple seconds to a couple minutes, depending on your data set. And that's why the compute preview is very helpful. So you can just quickly get feedback in terms of how good your parameters are and your input. So you can iterate pretty quickly. Okay, so let's say this looks okay for me for now. And let's now go ahead and apply post-processing to our segmentation. So we'll go ahead and use Watershed. So if you remember from our previous example, the first thing we have to do is create a gradient image. Then we just select all the materials, and I want a side-by-side segmentation result, and we click apply. All right, so this is now the result of our segmentation. So again, I'm not an expert here, but let's say this looks okay to me. Maybe we can do a bit of smoothing here, just to smoothen the edges. Okay, right, and let's say for now I'm okay with this, so we can actually preview the structures in 3D here. So this is the mitochondria, and then we have the other materials here. Right. And as usual, we can go back to the project view and generate the surface for our from our label images. And finally, create a surface view to view the 3D model. Okay, cool. And finally, let's just have a look and focus on the mitochondria. as you can see, that looks really nice. And yeah, so that's it for the texture classification, and I highly recommend it for more complex examples such as this one. Right, so that was our deep dive into the segmentation tools using Avizo. So are there any questions at this point? Okay, so as usual, you can post questions in the chat. So the next part of the workshop is a deep dive into the Ilastik application, which is an alternative segmentation tool. But before we go to that, maybe we can take again a 3-minute break. While we're in the break, maybe I just say a few words or a few things that might be helpful. So as I mentioned, I think in the first part, Avizo is a commercial tool. And we have a license for Avizo here at KAUST. So you can just download it from the IT website and set up the license. So the instructions are there in the IT website. And yeah, again, unfortunately, Mac OS is currently not supported anymore. So you can either use Windows or Linux. And if you don't have access to those to a machine, you can use IT's remote workstations, or you can also book our VR machine in the showcase that I showed earlier. So you can use that to use Avizo and then directly use virtual reality with Avizo. Because the other thing that I wanted to mention is that the TechViz application that I showed earlier, that also needs a separate license, and those licenses are installed only in the KVL's VR facilities. So if you want to be able to use Avizo directly in VR, you would have to go to KVL's VR facilities to do that. But later on in the last part of the workshop, I'm going to show you how you can use virtual reality on your own machine, but you would have to do a bit more steps than just a few clicks. And we'll see that in a bit, okay? And yeah, last thing, if you want to use KVL's VR facilities or the VR machine that I was talking about, you can go to our KVL website where you can book the spaces and the facilities. So just keep in mind that you would need your KAUST credentials to log into the booking system. And there's also a calendar there where you can see all the other bookings of the facilities, okay? All right, so I think that was the 3 minutes for our break. So I'll go ahead and share the video for segmentation using Ilastik. So far, we've seen the different segmentation tools that Avizo has to offer. And in most cases, these are sufficient to perform good segmentation. However, in some situations, you might be interested in trying out a different tool in order to try and improve your results, or you might simply not have access to Avizo. So in these situations, an alternative that you can use is Ilastik, which, as I've said before, is an open source and therefore a free application. And it's a quite powerful segmentation tool that is widely used in the research community. Now, before we go to the step-by-step tutorial for Ilastik, I just wanted to go through the documentation here, which is online, and I'll provide the link to this documentation in the workshop website. And I highly recommend going through this 3-minute video that shows you a quick example of how to use Ilastik. And I just want to go through it briefly to give you an overview of how Ilastik works. So the pixel classification or segmentation tool of Ilastik is quite similar to the texture classification tool that we used in Avizo. So in general, we specify manually selected or let's say a sparse selection of segmentation for our labels, as you can see here. And then this serves as input to the learning process that tries to learn a classification model that would then be able to discriminate the different materials in our data. And just like in the texture classification in Avizo, the first step is to select features that you want to use in the texture, or sorry, in the classification process. And if you remember, in Avizo we had 4 checkboxes to select features. So we had the statistical features and co-occurrence features. So in Ilastik, you have a bit more options over here and more fine-grained. So you have features that are related to intensity, to edges, and to texture. And for each of these rows, you have a corresponding column where you have sigma parameter per column. And the sigma parameter here corresponds to the sigma of the Gaussian that is used for smoothing the images before computing the features over here. Now, to give you an intuition on what these sigmas mean, we can take a look at the images over here. So if you have your input image over here, if you apply Gaussian smoothing with a sigma of 0.7, the result would look like this: sigma 5 and a sigma 10. And if, for example, you're trying to classify the cell outlines, so you want to detect or classify the cell outlines over here, in this case, sigma 5 would probably be the best feature to use, because the intensity values in this feature much better differentiates between the cell outlines and the outside and inside of the cells. So again, it would probably take a bit of trial and error to get an intuition of these sigmas and also the different features here. But the good news is that if your data set is relatively small, you can always just check all these features here, and the learning algorithm would determine the best combination of features to use. But later on, I'll talk about a way to try to pick an optimum number of features, because essentially what you have to keep in mind is that every feature that you use in here, or every feature you add to the learning process, contributes to the amount of time that it takes to perform the learning and eventually the classification. So you want to have that balance between the number of features here. So the more features you have, the better chances of getting good segmentation, but the whole learning and classification process takes longer, and the fewer features you have, the faster your classification and learning processes are. But you have, let's say, if they're not selected properly, then you might get poor segmentation results. Okay, so we'll get back to that in a little bit. And then just to quickly mention, you can pick to compute the features as in 2D or 3D. All right. And now let's say we've selected our features that we want to use. The next step just like in the texture classification in Avizo, is to specify your initial segmentation for your labels, as you can see here. So in Ilastik, you only have a manual brush as an option, but you only have to make a few brush strokes typically in order to generate good results. And once you have your initial samples, then you can get a preview of the classification results. And if you're not satisfied with the results, you can keep adding samples and even modify your feature selection if you want until you get a satisfactory result. And once you're happy with your classification result, you can then export the segmentation in the format that you prefer. And optionally, you can then upload that segmentation into an external application like Avizo for further post-processing and visualization. So now let's take a look at how we can use Ilastik to perform segmentation, starting with a simple data set. So this is the welcome page for Ilastik. And the first thing we have to do is click on pixel classification, because that's what we want to do. And right away, you'll be prompted to specify where to save your Ilastik project files. So I'll just go ahead and create a new folder here. Okay, and for this first example, I will use the SandCity data since we're already familiar with it, and it's a relatively simple data set. So the first thing we have to do is specify the input data, and we can do that on the right panel here. Click Add New, and since we're using an image stack, we want to use this second option here. And then we have to choose the files. So just click Control A over here, and choose option Z in here because we want to stack them across Z, and click OK. All right, and now the input data is loaded, so you can sort of zoom in a little bit here. And the next step here, as you can see, step 2 is feature selection. All right, so click Select Features, and so these are the features that I was mentioning earlier. So you can look closer here. So if you want to specify the options more fine-grained, but if you check the option or the main options over here, the check boxes below them or in their category get selected. Okay, so for edge, for example, if I click here, everything inside the edge gets selected. So you can do that if you want to fine-tune your features manually. But for now, as I said, if you're dealing with relatively small data sets, selecting all of these features is totally okay. All right, and the learning process will decide which of these features are the most optimal to use to get the best results. Okay, so for now, let's click OK. And a nice thing with Ilastik is that once you selected your features, you get the list of the features here, and you can click on any of them to get a preview of how the features look like, as you can see here. So let's see Gaussian smoothing, Sigma 10. It's very, very smooth, as you can see here. And if you look at Laplacian of Gaussian, this is more related to edges. As you can see, the gradient magnitude as well, difference of Gaussians, and so on. Right? So this is a good way of learning about the features and getting an intuition of what they are used for. Okay. So again, for now, we've selected all the features, and that's fine. And the next step is now the training, which is essentially assigning some initial pixels to your labels. So let me just rename our labels here to air and sand. Okay, let me just zoom in a little bit over here. So in Ilastik, you have to click on the active material here, and right away, if you click on the brush, whatever you brush on over here automatically gets added to your active material. So we can brush over here, and automatically that's added to the air material. And just like in Avizo, you can, or I highly recommend trying to get samples along the edges, because that would help the classification quite a lot. So now I switch to the sand material, and let's say I want to see how the classification would look like with these initial samples. You can click Live Update over here to get a live or interactive preview of the results. So this actually looks really, really good to me. And I mean, let's say I want to add more training samples. Let's say I can brush more over here. So you can see interactively the result gets updated. And let's say I'm happy with this. I can stop the live update and go to the next step, which is prediction export. So exporting your results. So we have several options here, but for today, I just want to export the simple segmentation, which already picks the most probable material for each pixel in our data. So let's just go ahead and click that, and we can choose the export image settings over here. So I will keep most of the options here unchanged. So what I'm mostly interested in is changing the file format, because let's say I want to upload the results to Avizo, and in my experience, one of the safest options is a PNG sequence. So we'll just go ahead and do that, and specify the output folder. So I'll just create a results folder here. So in case I want to generate more results later for comparison, and just click OK. And once you've done that, you can click Export All, and it should take a couple seconds to perform the export. And let me just go ahead and take a look at the folder. So we go to results 1. So as you can see, the images start to get exported here, and now it's done. So you might think that there's something wrong here because the images are black, but this is totally fine, because the Ilastik actually export the segmentation with the pixel values starting from the first label assigned to the value of 1, the next one is 2, next one is 3, 4, 5, and so on. So 0, just like in Avizo, is sort of kept for unassigned values. All right, so now let's go ahead and switch to Avizo to have a look at how our segmentation results look like in 3D. Right, so let's just select all the images, keep the default parameters, and as you can see here, it's basically an image stack where all the images only have values between 1 and 2. So 1 is air and 2 is sand. So before we can convert our segmentation into a 3D model, the first thing we have to do is to convert the image type. Okay, so right now this is just sort of a regular image stack, but what we want is to convert this into a label image, right? So we have to go here and click 8-bit label. And remember, a label image is the result of segmentation in Avizo. Okay, so let's just all right, so one thing that I have to mention here, and it's very important, is that when we do this, sort of importing an Ilastik result into Avizo, it's very important to uncheck this option here, because if you keep this option checked, what Avizo will do during the conversion is shift our labels so that they start from 0. And that means the air label will get assigned to 0, which means unassigned, and we don't want that. So let's just click apply. All right, and now as you can see here, we have our label images, and we can go ahead now and generate our 3D model from here. Let's use the default parameters, and as usual, use a surface view to view our results. Okay. So Avizo generated this default names for our materials. So let's say I just want to see the sand material. And as you can see, the results are really, really good. And we did this in just a matter of minutes as well in Ilastik. Next, we're going to take a look at a more complex example. So just like before, let's go ahead and create the Ilastik project file. And again, I will create a new folder. Okay, and this time we're going to use the heart muscle SEM dataset. And just like before, we're going to add our input data. Control A, open, stack across Z. Okay. Okay, now the data is loaded. We can go to feature selection, and let's go ahead and select features. Okay, so let's go ahead and for now, let's say we only manually pick some features. All right, and right now I'm just sort of doing this randomly. And later on, I'm going to show you a technique wherein we can ask Ilastik for features that it can recommend for us. Okay, so for now, let's just do this and click OK. Again, you can take a look at the preview of the features by clicking on the list here. And then let's go ahead and proceed to training. So we should just add some new labels. Okay, so let's go ahead and assign the labels to our mitochondria. Let me just increase the size of my brush here and start brushing. Okay, so as I said before, try to get the edges because some features are edge-based. So this would really help the classification to get good results. So you can also brush here, for example, and let's do a bit more over here. Again, I'm not expert in biology, so I'm just basing my segmentation here on the tutorial from Avizo. Okay, so now I want to select this region, so I probably want a smaller brush size. Okay. All right, so that was a few minutes of selection, and now let's do a live update and see what results we get. So that took a few seconds. So keep in mind that the more features you use, so the longer the learning and classification will take. So this is the trade-off that you have to balance. So right now, there's a bunch of errors that I see. So one helpful thing that you can do is, so you have a list over here, and you can enable the segmentation here, so you can see the segmentation more clearly. So for label 1, label 2, so let's say I think these are problematic regions that I want to correct. So let's correct this one first. And this is with live update enabled, so as soon as I add new brush strokes, okay, the results would get updated. So you have to wait a bit per brush stroke. So there you go. So that improved my result a bit, and let's just brush more over here. Okay. So as you can see, it's already taking quite a bit of time to perform the learning and classification. And that's why it's important to just select the features that you think would be helpful. Okay. And nice. So this one I think looks pretty good. Okay. Again, I'm not an expert here, so let's say for now we're happy with this one. So okay, let's just stop the live update. And what I wanted to show you next is this suggest features option. So let's just go ahead and click that. And here you get a window in where Ilastik can help you pick a fewer number of features that would try to get results that are as optimal as possible. Okay, so there's the steps are over here, so I won't go through them in detail, but in general you can pick a method here for the recommendation. So we'll just pick the recommended one, and also keep the default number of features, so you can decide how many features you want to have in the end, and then just click run feature selection. Now this sort of feature recommendation can take quite a long time, because what it does under the hood is it tries a lot of combinations of the different features and tries to figure out which ones would produce good results. So this can take quite a bit, but it's usually worth it, especially if you're going to perform the classification on a really big data set afterwards. So I might fast forward this part just to reduce our waiting time. All right, so now the computations for figuring out the recommendations are done, and the important part to look at here is this drop down over here. So let's go ahead and click that, and right now you see 3 rows. All right, and what you see here, so the top one, it says user features. So this top corresponds to the results based on the features that we currently selected. Remember, in the beginning we selected some features, and this gives you the sort of the error that you get using our features. So the lower this error is, the better. And this is the computation time in seconds, so how long it takes to perform the whole process. So here it's 21 seconds. And in the middle, or in the second row, is the recommended 7 features. Okay, so later on we can take a look at, okay, what are these 7 features that Ilastik recommended? And the error is 0.053, so that's really low, and it's actually lower than our error, so the results of this one should be much better. And remember, our features, I just kind of sort of selected the features randomly. So this one, using this tool has paid off, because the error that we're going to get if we use these recommended features is lower than the error that we would have gotten if we used the randomly selected features. And also the computation time is reduced to 14 seconds instead of 21 seconds. And just for comparison, usually this tool also shows you the results if you used all the features, okay, that are available. So of course here the error is a bit lower, so it's 0.028. But if you look here, the computation time is almost double that of the recommended option. So here you have the option to pick which one you want to use, and of course we want to use the middle option because we want to be fast, but still with good or with low error. So let's go ahead and do that. So once you click that, you get a preview here of the segmentation results, and you can also show the feature names. So what features it decided to recommend to us. Click OK. And let's say now we're happy with this feature set, so let's click select feature set, and that should select them here. So as you can see, now there's just fewer features here compared to before. Let's just click OK. Now we have to click live update again just to update our results. And finally, we want to export the results as a simple segmentation using a PNG sequence format. And now let's specify the output directory. And click OK. And export all. So again, this might take a bit of time. So let's just go ahead and open the folder here. All right, so now the export is done, and once again we can take a look at the results in Avizo briefly. Same process. So we can first convert the image type to 8-bit label. So just a quick comment, if you have more than 255 materials, so you should use 16-bit and then 32-bit and so on. So for now, let's use 8-bit and uncheck clean labels, click apply. And now we have our label images here. All right, and now we can click generate surface and just click apply. And finally, a surface view. And now we have our nice 3D model here. All right, and this is the first material in our list. So just another thing that I wanted to show quickly is that once you have your segmentation in Avizo, you can perform some post-processing to it using the segmentation editor. So you can click that over here. Okay, and for instance, you want to perform smoothing or filling holes, you can do that over here. So let's just say I want to do a tiny bit of smoothing, then I can go ahead and do that here. Or if I want to, let's say, remove islands. Okay, so let's say I want to remove like tiny islands with size 15 voxels in 3D. I can do apply. Okay, so this sort of edits the segmentation, and these are edits that I couldn't have done easily in Ilastik. So with that being said, I want to emphasize that this whole process that we did of segmenting in Ilastik and then importing the results in Avizo, it's not necessarily a linear process, right? So the great thing about these two tools is that you can switch between the two, and one can go before the other. So for example, you can perform pre-processing on your raw image stack in Avizo first, and then export the pre-processed image stack, let's say as a PNG sequence, load the PNG sequence into Ilastik, perform segmentation there, export the results, and import them back in Avizo. So these two tools can be quite powerful, and once you've gained an intuition on the more important tools and features in these two applications, then I would say you would be well equipped to perform a lot of different, or I mean to perform segmentation on a wide variety of data sets. Right, so that was our tutorial on using Ilastik for segmentation. So for those of you who are interested in doing, let's say, more sophisticated type of segmentation, let's say using deep learning. So Ilastik actually has a beta version where you can now sort of use deep learning for segmentation. And Avizo also has a way to use deep learning for segmentation. But we won't cover that in this tutorial. We might have a workshop in the near future where you can learn more about that. So it looks like there are no questions. Again, if you have questions, just post them in the chat. And yeah, I'll go ahead and play the video for the next part, which is 3D reconstruction. Let's now talk about the 3D reconstruction step in our workflow. You probably noticed that we've actually been already doing 3D reconstruction in our previous step-by-step tutorials, where we converted our label images into a 3D model using the Generate Surface module in Avizo. So for this part, or in the next few minutes, I will show you some more options that you can use in the Generate Surface module, and also show you some options for post-processing the 3D model, such as extracting subsets from the generated 3D model, and also reducing the triangles in case your model gets too big for interactive processing and visualization. So I went ahead and loaded a project that we created earlier, where we segmented the sandpack CT data, and we got this segmentation result. And we've already used the Generate Surface module to perform the 3D reconstruction, and that gave us the 3D model over here, which is currently being visualized in our 3D viewer. And the first thing that I wanted to show you is how to export the 3D model. So we can click here and then click the export button. So we can click export, then you can pick a folder where you want to save your 3D model in, and specify a name. Let's say I want to call this sandpack model, and then you can pick a format that you want to save your model in. So you can pick a format that would be most suitable for the external application that you want to use for your model later on. But for now, I will use the Wavefront OBJ format, which is a widely used format for simple triangle meshes. So I will just click Save. And now if you go into that folder, you get your file for your 3D model. And if you're using Windows, if you just double click the file, the 3D viewer will actually show you your model. And as you can see, this doesn't look interesting aside from the hole over here. And that's because we actually exported the whole model here, which includes both the sand and air material, and therefore we can only currently see the outside triangles in the model. And one way, or like the best way to solve this, is to extract either the air material or the sand material mesh. So in order to do that, we can use the surface view and use the same approach as we did before to decide what parts of the mesh will be visible. So in this case, let's say I just want to extract the sand material, so I can add that to my surface view buffer, as you can see here. And now what you do is you attach an extract surface module to your surface view. And as the name implies, what this does is whatever subset of the mesh is visible in your surface view, it will get extracted and saved into its own object here. And therefore, if you extract this particular model, so let's say we call this sand model and use the same format. Okay, this should now allow us to just load the mesh for the sand material, as you can see here. Okay, and so here you can also change the shading parameters, for instance. And later, we're going to use this extracted 3D model for visualizing our data in virtual reality using the Unity game engine. Let's now take a look at a more complex example. And for this one, we're going to open a new data set, which is a core sample CT scan. So let's go ahead and create the data object. All right, so for this one, we can have a quick look at the data using volume rendering. So you can see the rock sample that we're interested in over here. So we'll go right away to segmentation. And for this, Avizo actually automatically picks a good min-max threshold for my thresholding tool. And I'll just go ahead and use that. Of course, you can use more complex segmentation steps if you want, but for now, our focus is the reconstruction and not the segmentation. So let's say we're happy with this resulting segmentation, and we'll go ahead and add a generate surface module. So this time I just wanted to quickly go through the options that you have in the generate surface module, so we can actually open the documentation related to this module, so you can have a read at how the module works, and also what each of the parameters do. So the first option you have here is Compactify. And as you can see here, if you check Compactify, a post-processing technique is applied to the resulting model to reduce the number of triangles. And the minimum edge length is a parameter that is used to control the triangle reduction. Okay, so you can go through the details of the algorithm here. All right, and you can pick to choose here repeatable or fast. So repeatable only uses one thread and assures that even if you apply this algorithm on a different computer, you'll get the same results. While if you use fast, obviously it will be faster, so it will be parallelized, but it's not guaranteed that you'll get the same results if you use a different computer. Okay, and for the border, if you want to generate triangles for the border material, you can check this so that you don't have holes in the border. And by default, a smoothing is applied to the label field before the mesh is generated in order to avoid jagged meshes. Okay, and you can adjust the smoothing parameters here. Okay, so for now, let's try to generate our 3D model from our label field. So as you can see here, because the data set is relatively big, we get a warning from Avizo that says the resulting mesh would probably be pretty big. But in this case, I'm okay with that, so you can actually click continue, and this should give you a mesh. It will take maybe a couple seconds to generate the mesh, as you can see here. So now, as usual, we can create a surface view to visualize the mesh, and we can turn off the volume rendering so that you only see the mesh, and also let's turn off the ortho slice. So this is now the mesh of our rock sample or rock material, and if you look at the surface object over here, you can actually get some information about the resulting model. So it says here we have around 2 million points and around 4 million faces, or 4 million triangle faces. Okay, and for some applications this might be okay, but let's say for your application this might be too much, so it might be taking too much time to render or to process, so you want to reduce the amount of points and faces. So one way to do that is by using the simplification editor in Avizo. So if you just click here while the surface object is selected, you get these options here for simplifying your mesh. So simplifying just means reducing the number of triangles while trying to keep the general structure or shape of your object. Okay, so I find myself mostly just using this faces parameter here, so you can specify the number of triangular faces that you want to have in your output mesh. So you can also specify the maximum distance and minimum distance of the edges, and there's other options here that I won't get to in detail for today. So let's say I want to reduce the number of faces by order of magnitude, so we can give or specify the parameter here as, let's say, 400,000 instead of 4 million, and we can just click simplify now. So just keep in mind that you can specify the sort of target number of faces here, but the result will most likely not be exactly the same as your specified parameter, but it will be around that number. Okay. All right, so that's it. So you probably did not notice that something changed here, but the model actually was already simplified. And if you now look at the number of faces here, we have roughly around 400,000 faces. And you can actually have a look at the, say, the triangle faces over here. So if you zoom in, you're going to see how the triangle faces look like. And now let's say I want to reduce this further. So I just want to show you how it looks like if you now, let's say, want to reduce this further in half. Let's just go ahead and simplify. So notice how the triangle faces changed. Not sure if you saw that, but the triangle faces basically got bigger. And if we keep on doing this iteratively, so just, okay, so now you see that the triangle faces got even bigger. So we have much fewer triangles than before, but as you can see, the quality is still okay. So again, the amount of reduction or simplification that you want to apply would depend on your needs and your application. Okay, so for now, let's say I'm pretty happy with this one. So we can go ahead and export the model. So as usual, I can click here and then click export, and let's say, okay, specify a name and the format, right, and I can save. And just like before, we can go to the folder and try to open it and see how it looks like. So if you have other 3D modeling tools, for instance, you can also use those to have a quick look at your result. So with the sand CT example, we've seen how to extract subsets of our 3D model by selecting different materials. But in this case, we only have one material, which is the inside material, and that corresponds to the whole rock. So we can't use that easy approach, but we have an alternative way to extract a subset of triangles coming from the same material. So for this particular example, let's say I just want to extract this part of the rock. So what we can do is use this show hide tool. So whatever is highlighted, whatever is highlighted inside this box over here, we can go ahead and actually add it to the buffer. But before we do that, so okay, let's have it selected here. We can then just clear the contents of the buffer and click the show hide again. So I cleared the buffer because if you can remember, whatever is in the buffer will get extracted later on. So I cleared it first, and now we can highlight what we want to add to the buffer. So let me just add this. So there's some extra stuff here that I don't want. And in order to get rid of that, I can actually go ahead and click our surface object and click the surface editor. Okay, so with the surface editor, we have a bunch of options here for adding, subtracting, and clearing the buffer in our surface view. And our goal here for now is to remove the extra triangles here in the bottom. Okay, and we have tools over here that allow us to select triangles. I will not go through all of them in detail, but some of the tools that I typically use is the magic wand. So if you click on your model, it will select triangles in a connected region. So then you can remove those from your buffer, for instance. So I can do the same for these ones, or I can use the draw contour approach. So just like the 3D lasso that we have for segmentation, you can draw a contour to pick the triangles that are inside the contour and then just remove those. Okay, so let's say right now I'm happy with this selection. Then I can go ahead and close my editor, go back to surface view, and just like before, we can add an extract surface module, click apply, and we should now have our extracted surface, and we can export the model. Say I'll just call it top rock and save it as a wavefront obj. Okay, so just like before, we can have a quick look at the model. And yeah, as expected, we only have the top rock or the top part of the rock sample. So that was the reconstruction part in the workshop. And now we're going to go to the last part. And this is around 35 minutes. And here we will talk about how to use the Unity game engine to sort of build a very simple VR application in 30 minutes or even less. And just keep in mind that this is sort of a quick hack, just to show you that you can use existing plugins or existing assets in Unity to just quickly build a prototype where you can bring in the 3D model of your data set in virtual reality. So this next part is very helpful just in case you don't have access to the Avizo plus VR option, or if you want to build kind of a different experience for your data set. So I'll go ahead and play the video. And as usual, if you have questions, just post them in the chat. Next, let's talk about the visualization step in our workflow. As you have seen in our workflow overview earlier, we were able to bring our 3D model into virtual reality using Avizo directly in connection with the TechViz application. And in just a few clicks, we were able to visualize and interact with our 3D model in VR. The next thing that I wanted to discuss is how to use an alternative application called the Unity game engine to bring our 3D model into virtual reality. Now, before we get into that, I just wanted to quickly mention the main differences between the two approaches. If you use Avizo to bring your 3D model into the virtual world, then you still have the option to perform analysis on your data using the powerful built-in modules of Avizo. So we can say that the Avizo approach is more data-centric and analysis-oriented. On the other hand, if you're interested in bringing your 3D model into a virtual world and allowing your 3D model to interact with the virtual environment, as you can see here in this preview, then Unity would be a better option to use. All right, so now let's go ahead and have a quick look again at how we can use Avizo directly in virtual reality. Here I have my RockCT project opened, and I added an orthoslice and used the orthoslice to clip my surface view. We create the TechViz connection object in Avizo, and then start the TechViz controller. Make sure that the headset and controllers are detected. Click the VR icon and then the Avizo window. And in the TechViz module, click Connect and then Autoscale. Now you can lift the VR headset to your head height, and then click the center button to move the model in front of you. And then you can now put on your VR headset and grab your controllers. You can now click the grab button or use the grab button to bring the model close to you and move it around, and use the trigger button to directly interact with the modules in VR. And as you can see, in just a matter of a few minutes, we are able to switch our visualization and interaction from the desktop into virtual reality. And now we can open any of the open modules in VR so that we can change some of the parameters directly in VR without switching back to our desktop. For example, here we can change the slice orientation. So just keep in mind that you can use any of Avizo's visualization modules directly in virtual reality. Next, we will take a look at how we can use the Unity game engine for VR visualization. Now, before we go into the hands-on tutorial, I wanted to show you first some of the components that we will use for today and give you an overview of how they're all connected. So the main application that we will use for today is the Unity game engine. And for those who are not familiar with Unity, it's an application that you can use to easily create 2D and 3D games. In addition to Unity, we'll also use a partner application called Unity Hub, which allows you to manage all your Unity projects and different versions of Unity installations that you have in your computer. Furthermore, we are going to use Steam VR plugin, and you would have to install Steam VR on your computer and download Steam VR plugin into your Unity project in order to communicate with your VR device. Now, in our case, we are going to use an HTC Vive Pro for this particular tutorial, but with just a few changes. The whole process should also work for other VR devices such as Oculus and Windows VR systems. Finally, you have your 3D models that you can then bring into your Unity game or application. And in our case, since we want to use VR for data visualization, our 3D models would include the models corresponding to our datasets that we segmented and reconstructed using Avizo. In addition to these data models, we can then also use other 3D models to create a virtual environment where we can explore our data. For instance, we can create a virtual laboratory or virtual office, or for example, if you have 3D models of corals or other underwater structures, you can create a virtual underwater scene where you can explore your data. The nice thing about using Unity for VR data visualization is that you have more room for creativity in terms of how you let your users and other stakeholders experience your data and tell your story in a more engaging and immersive way. In today's tutorial, instead of building a virtual environment from scratch, we will actually use a pre-built virtual environment from the Steam VR plugin, and you can sort of see that virtual environment here. And you can think of it as some sort of a virtual lab or virtual office. And what I'm going to show you is how to quickly bring your 3D model into this 3D environment and allow the users or the players to interact with this data model by grabbing it and moving it around, and also letting the model interact with the different objects in the environment. So the steps that I'm going to show you in the next few minutes is not the only way to do things or to implement things, but in the interest of time, this is the approach that would probably be the fastest and easiest to do. All right, let's now switch to our step-by-step tutorial. And at this point, I'll just assume that you've installed Unity Hub, Unity, as well as Steam VR. And right now I have Unity Hub running. And we'll go ahead and click New Project to start a new project. And here you have the option to start from a template that's predefined by Unity. And if you're using VR devices such as Oculus or Windows VR, this VR template would be the fastest or probably easiest to use. But in our case, since I will be using an HTC Vive and using the Steam VR plugin, it would just be cleaner to start with an empty 3D template. And here we can go ahead and specify name for your project and the location where you want to have your files, and just click Create Project. So this will automatically start the latest version of Unity. Okay, so as soon as we started Unity, we get this sort of default window configuration over here. And unfortunately, we don't have time to go through everything in detail, but I just wanted to give a quick overview of the main parts that we will use for today. So on the left, you have your hierarchy view, where you can see a list of the objects that you have in your scene. So for example, here we have your camera and the light, which were created by default. And here you can add different objects to your scene by, for example, clicking right-click and create a 3D object, for instance. And later on, I'll show you different ways to add objects here. And in Unity, the things that show up in your scene are called game objects, as you can see here. So for example, I can create a cube game object. You see it here. And here in the middle is our scene view, which shows us how our current 3D scene looks like. And if you click on any game object here in your hierarchy, you would see the properties or the parameters of that game object in the inspector window. So this is a little bit similar to the project view and the properties view of Avizo, if you remember. Okay, so as I mentioned, everything in Unity is a game object, or all the items that you can add to your scene are game objects. And your game objects can have components, as you can see here. And a component would typically be some sort of feature or capability that your 3D object can have. So you can have, for example, here colliders for performing collision detection. You have a huge list of components that Unity provides. And you can also create your custom components. And typically this would involve a little bit of programming. So with that being said, you can create components that are based on some script that performs, let's say, compute operations and different programmatic things by using the script and programming. But again, we will not really dive deep into that part of Unity, and we will just try to complete our task with very minimal to no programming at all. Moving ahead with different windows, you have your project view here, which is like your way to explore the different folders in your project. And if you click on any folder here, the contents of that folder show up on the window on the bottom here. All right, and since this is a game, once you're ready to take a look at the preview or to run your game, you can click this play button over here, which should bring you into the game view. So you can think of this as the view that your player will see once the game starts. And you can use this for debugging, for example, and testing. And very important feature is that you can switch while on a game mode. You can switch to the scene to sort of make any modifications like translate, rotate, and changing the other parameters of your game objects while your game is in preview mode. But just keep in mind that whatever changes you made, once you've stopped the play mode, the changes will be reverted. So you'll have to redo them again if you want to keep the changes that you made. Okay, so now I will just go ahead and delete everything in my scene and go to Window, Package Manager. And now what I want to do is to import the Steam VR plugin. Now, Steam VR plugin is a free plugin that you can download from Unity's asset store. So if you actually, let's just close this for a minute. If you click here, there's an asset store, which is now online. And it's basically a website where you can download different resources for Unity so that you don't have to do everything from scratch. And I will skip that part. And basically here I already downloaded SteamVR plugin, and I would just go to the package manager, select my assets here, click SteamVR plugin, and click import. So here we just keep the default of importing everything and click import. After the import, we'll get a bunch of pop-ups here that tell us, okay, Unity has to be restarted. So just click OK. And now in the other pop-up window, we're asked if we want to accept the recommended settings by SteamVR, and we'll just click accept all. Nice. All right, and I won't go through the details here, but now in the XR plugin management window, we have the OpenVR loader added and selected for us. And if you're using other VR devices like Oculus or Windows VR systems, you would probably have to select the other options. But again, that's out of scope of this tutorial. So we'll just go ahead and close this, and close the package manager and go back to our scene view. And now what you would notice is that there's a bunch of folders added to our project, which are from our SteamVR import. And here, what I want to do now is actually look for the example scene here. So I will just get rid of the old or the initial scene that we had. So I opened this interactions example scene that is provided in the SteamVR plugin. As I said, we will not build a virtual environment from scratch, but rather start from this provided example. And in any case, when I build or when I want to build some simple VR application, I sometimes even copy this scene and start from there and just delete the stuff that I don't need and reuse a lot of the scripts and components and game objects that are already here. So for instance here, we can already go ahead and actually play and experience this scene in VR. So let's just go ahead and see how that looks like. So let me just connect my VR system. Okay, so make sure that your headset and controllers are or have been set up properly, and then now you can click play. And okay, so we actually get prompted about the SteamVR input setup. So here you can just click yes for now. Again, yes. So this is for the configuration of the controllers. Okay, so we just click save and generate, and then close this. So let's just click play. And now I should be able to put on my VR headset, okay, and hold my controllers. And then, right, now I'm in my game, so let me just hold the two controllers over here, and let me just check that, yeah, so you can see what I see through the Unity window. And here, we're basically in the virtual world that SteamVR plugin provides, and we can teleport around, okay, and interact with the different game objects here. So for example, I can grab and rotate that object there, and I can go to this area here with the tables and the different objects that, if you read the description, you should be able to grab and hold them. and move them around, drop them. These objects, as you can see, can interact with each other and interact with the virtual world. Okay. So what we want to do is do the same thing with our with the 3D model of our data. So let me just stop the preview, and now what I want to do is just keep using this scene and go to this area over here and add our data model, let's say, on this table, so we can interact with it. And what I would do right now is some sort of a hack or a really quick way to bring our 3D model into this world and be able to interact with it in just a matter of let's say a few minutes. And what I would do is I will go ahead and click on an object, a game object, such as let's say this sphere over here, that already has the behavior that I want my data model or the 3D model of my data to have. Okay, and that is being able to interact with the virtual world and being able to grab it. And what I'm going to do is basically keep the components of this game object. So as you can see here, I clicked on this game object that I want my data to have similar behavior. And you can see here the different components that it has. And we won't go through all the details of these components here, but essentially what these components do is it gives this 3D model the behavior that we saw earlier of being able to interact with the world and being able to be grabbed and moved around by the virtual hands. And what I'm going to do is just a hack where I would replace this 3D model with a 3D model of our data set. All right, and what that would do is essentially give our the model of our data set the same behavior as this game object. So let's go ahead and try that. So let's click this game object, and you would see in the hierarchy window that the object gets highlighted. And if you look at this game object, that's the throwable object. So this is an object that's been created or that is within the Steam VR plugin. And we're just essentially modifying it so that we can use it for our purposes. And a child of this throwable game object is the sphere 3D model, or the game object that contains the mesh, okay, of the sphere and some other components such as collider, which allows for collision detection, and the renderer of the mesh that allows us to see the game object, and also the material over here, which tells the renderer how the object should look like. All right. So again, our goal is to replace this sphere game object with our data game object. Okay. So in order to do that, the first thing we want to do is to bring our data model into the Unity game engine. Okay. And I would just first create a folder where we would put our data in. So let's just create a folder called data, double click that. And now let's go to the folder where we have our, we have the 3D model of our data. Let's say I want the rock core sample, which is, we exported it from Avizo in the OBJ format, if you can remember. And I just simply drag and drop it into this window in Unity, and it actually shows up here right away, and that's quite fantastic. So that's how easy it is. And now what I'm going to do is to drag and drop now this object here into the throwable game object here, and you can double click on the the rock game object to see where it is in the scene. And as you can see, it's actually been imported, but it's gigantic compared to the size of our scene. Just to rescale our object, we can actually change the transform over here. But before we do that, I actually want to point out that, yeah, so the game object that we created here also has a child, which actually contains the mesh that we're interested in. So what I want to do is to bring out this mesh and make it a child of the throwable. So let's just try to do that. So if you try to do that, you get this prompt that says you have to unpack the prefab. So I don't have time to explain that, but for now, what you have to do is go to prefab and click unpack. So that allows me to split up and move the game objects around. So here it seems like I have to do that for the throwable prefab as well. Unpack this prefab as well, and yeah, because the throwable was also a prefab. So we can now delete this parent. Anyhow, we have this mesh of the rock. We can rename it to rock, and we can now rescale it. So you can use this button here to rescale along X, Y, and Z as you wish, or X, Y, and Z, or you can also change directly the scale here. Let's say 0.01, 0.01, 0.01. And now we can see it got smaller, but maybe it's still not enough. Let me just change the translation here, or the position. So this is the position with respect to the parent. So I will just set this to 0 so that it gets centered with respect to the parent, which is the throwable. Okay, and since it still looks too big for me, we can go ahead and further rescale it. Let's say, okay, perfect. So this actually looks good to me. And yeah, now the rock sample is placed in our virtual world, and I can actually just move it a little bit here. We can remove the sphere. Remember, we want to replace it, so we can actually disable the sphere object and make it disappear by just unchecking here. And now we have our rock object. And the next thing that we have to add to our game object is a collider. So if you look at the sphere object here, it has this the mesh filter, the renderer, and the material here. But it also had a collider that is used for collision detection, and that's crucial for grabbing, for example, and interacting with the world. So here, if we look at our rock game object, we also have the mesh filter, the renderer, and the material, but we don't have a collider. So to add a collider, we can just go here to add component and search for collider. So you have different predefined collider shapes, and for our model here, a capsule collider sounds like the best option, and we should try to actually change the shape of our collider. Okay, let me just we can change the direction. Okay, So we have to try to match it as much as possible to our object. So okay, let me just, all right, and then we can shift it around by changing the center. Okay, so I can just, I want to line it up nicely. So you can click here on the parameter and just drag, click and drag. Okay, that looks okay to me. It's not perfect, but for our example, let's say it's fine. And now let's go ahead and try this out and click the play button. Okay, so let me go ahead and put on my VR headset and grab the controllers. Okay, and now I can teleport close to the table, and here we see our rock sample, and I can just grab it and basically try to hit the other objects around. As you can see, the grabbing is not perfect, and it's still sort of based on the sphere object that we had earlier. And I mean, we'll see if we have time to fix that later on, but for now, what I want to fix is this sort of hole that you see here, that it looks like some part of the rock is missing. So let's go ahead and drop it back in the table and go back to our desktop. So now we can stop the game preview and try to figure out how to fix this hole over here. All right, so let's go ahead and try to solve this these missing triangles from our model. And if you remember from when I was talking about the surface view in Avizo, this problem actually comes from the fact that by default, or the standard shader in Unity calls away the back-facing triangles for optimization purposes. So what we want to do to solve this is to disable this back-face culling in Unity. And in order to do that, we actually have to change the material that is used to render our rock model. So let's go ahead and create material. Okay, let's call it rock. And inside this material, you can select the shader that describes how the rock material will be rendered. And in our case, we want to create our custom shader that is based on the standard surface shader. So let's just call this rock shader as well. And then we can drag and drop this shader into our material. So it gets assigned as the shader here. And we'll go ahead and edit the shader. So if you click the edit button here, your default code editor, or it could be Notepad as well, you can use it to modify the shader. And shaders, I would say, or the details of shaders is out of scope of this tutorial. But what I just want to point out for now is that this is using Shader Lab, which is a Unity-specific shading language. And for us, what we want to do is just add basically a variable here, or set the variable culling to off. Okay, and that's it. And we just add it here together with the other properties here. Again, we will not go to the details of the shader. We just want to specify that, okay, for the shader, we will turn off the back face culling. Okay, so you can go ahead and close the editor if you want. And now we should be able to drag our new material into our rock object in the scene. And as you can see, the hole gets filled. And we basically fixed that issue. And if you want, we can go ahead and go back to VR and have a look at the correct version. So let me put on my headset again, grab the controllers, and like before, we can teleport close to the table where we have our rock model, and we can go ahead and grab it and have a look around. And we can inspect it closely. So if you imagine this is my virtual lab, I can basically put my samples all around this table and maybe annotate them or rearrange them somehow. And if you're telling a story, for example, you can let users get into this VR world and let them play around with your different rock samples. Or if you have a collaborator who cannot travel, for instance, then you can set up like a virtual collaborative world where you can explore your different data sets. Right, so that was the last part of the workshop, and hopefully we were able to give you some general overview of the whole workflow for segmentation, reconstruction, and visualization, mainly using Avizo, but also using Ilastik and the Unity game engine. So are there any last-minute questions from the audience? So just wanted to remind everyone that we will post the recording of this workshop in YouTube, and you will find the link in the workshop website. So with that, I wanted to thank you, everyone, for attending the workshop. And if you need any help with data visualization and data science, please feel free to reach out to us. Again, thank you, and have a nice evening, everyone.